Today, we're going to take a look at how to analyze your DPC++ design. In particular, we want to analyze FPGA early imaging. This lecture is a part of the DPC++ tutorial series. There are several steps we need to perform in order to have a highly optimized design. First stage, usually it is emulation stage. So you will compile your DPC++ program to FPGA emulator. This is to make sure that the design is functionally correct. And this compilation usually is very quick, takes seconds or minutes. And then through this compilation, the compiler will generate reports. So that's the second stage. We will look at the report, look for bottlenecks, and revise the design if necessary. Once we're satisfied with the design, we will proceed to the third stage, which is to generate FPGA binary. This compilation process takes a much longer time, usually in hours. Eventually, you'll have an FPGA bitstream generated for your target device. So we can take the binary and execute it on the FPGA card. And finally, we will run profiling to analyze the design's runtime performance and to, again, confirm whether our design meets the function and performance requirements. In today's lecture, we will look at essentially the second stage, how to read the reports generated from the emulation compilation and try to make sense of these reports and identify any bottlenecks. Now we'll have a demo about how we can generate reports and how we can open up the reports in the VTune file. Open up the reports in the browser to analyze the compilation report, to analyze the reports on FPGA's early image. Once you have the reports generated, it's usually in the format of HTML file named 8report.html. In this example, we use one of the implementations of matrix multiplication in our source code. Once you have the report generated through make, you can find the report file by opening the folder created underneath the build directory. So in this case, it's matrix multiplication -para, stands for parallel -v1 _report.prj/reports/report.html. When you open up this file in a browser, you will see there are several information panels show up on this web page. And on the very top, you have a few buttons that will take you to different groups of information analysis report. We'll start with summary. The summary page shows the basic compilation info, along with the kernel summary, clock frequency summary, resource utilization report, any warnings, etc. So if you click the kernel summary, for example, as we see here, this will tell you the project name and the target device family, the board name, and the SQL version it's based on, and the time that this report was generated. For the kernel summary section, you see often the time the names of the kernels that you have. In our case, we only have one kernel, so that's the name of the kernel. And that, if you notice, this is the class name we give to the parallel 4 kernel function when we create that kernel. The source location, if you click, that will take you to the corresponding lines in the source code. And also it shows some default numbers, the compute units for FPGA is always the case. It's a 1 unless you create multiple compute units. The target frequency is not specifically specified, so the compiler tries to match or achieve the maximum frequency possible. And on the same page, on the right side, there is a panel showing the source code. And you can click this section part here to go to different source code file. By default, it opens up the header file like we have here. This is still the first summary page. If you click the system resource utilization, you will get a list of the resources that are going to be used by your design. These are reported by the compiler. For example, for adaptive logic module, there are close to 427,000 units of this ALM, and the static partition means the compiler will decide to use about 90,000 of those in your design, and also it lists the utilization of other resources. And this kernel system are additional to those, and those are reported, used by your specific kernel function. The other interesting panel that you can bring up is the system viewers panel. If you click this, that will show you a drop-down menu showing graphic viewer, kernel memory viewer, schedule viewer, etc. And in this particular snapshot, we show the graph viewer. When you click graph viewer, that will show something like this. On the very left, this is the graph list where you can click to choose illustrate the whole system design. That means all the parts in your kernel, or you can choose individual kernels. In our case, we only have one kernel function, so if you click system, that will show the only one of the kernel function we have in the design. And then also within this graph list, you can see there are different entries listed under this par v1 kernel, and from the icons you can infer the types of these objects. So class 1 is the combination logics, and you may see other, for example, memory components, ROM or RAM, pipes. So all different types of components that are used in your design are going to be listed here. For this particular design, what we see here is this is our kernel, and this is inside FPGA, and because we load data, that is the matrices, from memory, so you see this global memory here, and there are links connected, so these links are connected to the memory to represent the load or store unit, and that will be used by your design to load data and store data. And if you click these modules, you will be taken you will be taken to the corresponding segments in your source code. Now we can zoom into one of the modules in your kernel design. In this example, we have B0, B1, B2, 3 modules, and you can click any one of them. In this slide here, we show what we have in this B2 module. So we have a few interesting blocks here. Cluster 2, cluster 3. These are combinational logics that making up that your design is made of. And also we have a few circles and arrows here. These are related to the loops. So we have loop input, and then incrementing the counter, comparison with the loop iteration variable. So these are part of the control path that used to implement the loops. And LD is the load unit, which is used to load data from memory component. In this design, let me go back here. In this design, we see the whole picture. So if you click this kernel, and if you change this drop-down menu to show the .cpp source code, that will point you to the exact location of the kernel function, which is encapsulated in this parallel 4 lambda function. Now, in the previous design, we didn't have this unloop, this pragma unroll factor. The unroll factor is a way to increase the efficiency of loop operations, especially if there's no dependencies of these loops. And with this unrolling, we can use replicas of the design to basically replicate the loop iteration and use more resources to take advantage of the parallelism. So essentially, we are using this unroll factor of 4 to increase the number of load unit from 1 to 4. So that's why you see 4 here, so that we can load 4 of these vector elements from these rows or columns, instead of just loading 1 at a time. So essentially, the number of loop iterations is going to be reduced by a factor of 4, but each loop iteration will use 4 times of the resources before the unrolling. This is another design. So what we show here is the single task. The difference, the major difference between this design is that we use handler single task instead of parallel 4 in the other 2 previous designs. We're going to talk more about single task, but the main reason we use single task is that parallel 4 will rely primarily on the runtime to schedule the launches of the kernel instances. For the case of FPGAs, it's harder for the system to optimize the kernel instances such that they will utilize the memory controllers efficiently. As a result, for FPGA designs, the recommended way is to use single task, and with single task, we can focus on this one single task kernel to optimize the memory accesses, and so that we don't have to rely on the default scheduler to schedule these memory accesses from multiple kernel instances. And in this example, we use single task, and we also have inside this kernel function, we go through all the rows and columns, and for every innermost loop, we do a unroll factor of 2. So if you look at this design here, we will see this 2 times of the load unit. So we can load these vectors 2 at a time. So, load these elements from the vectors 2 elements at a time. Next example, we have additional loop unrolling factor here, and this is for unroll the outer for loop. And we're going to still keep this unroll factor of 2 for the innermost loop, but the outer loop, which essentially goes through all the rows and columns, we do unrolling factor of 4. So from looking at the design, and this is the whole design, what we show here is that we're going to see 4 of these modules because of this unroll factor of 4. And within each of this module, we enlarge that here, you can see that this 2 times of load store unit, and we have 2 of those because we have an unroll factor of 2. From these several examples, we just want to show that how your design in the kernel function can drastically change the internal design on the FPGA. And this again shows that there's a lot of flexibility for the programmer to do through high-level language programming to have an influence on how the FPGA's hardware resources are used to formulate the design.